Hello, chemistry students. Today I'm going to be going ahead and reviewing some of these problems with you to kind of get you ready for the test and to make sure that we have some review time with some of these concepts. So first and foremost, what you will see is a few of these slides with convection, conduction, and radiation. Before I go through these, I'm going to review these concepts with you just to make sure that we all know what they are, and then we will go ahead and we'll look through this one. So just as a quick review, we have we're going to go ahead and we're going to start with, I think we're going to start with radiation first because radiation is pretty simple. Okay, so first of all, we have radiation. And radiation, you have to keep in mind, it's transferring heat energy without touching something. So it's going to be a transfer without touch. So it is going ahead and doing that. So an example is the sun. So the sun is a huge example of radiation. And the sun, you can still feel the heat from the sun from far away, right? But you don't touch it, right? And you don't have molecules that are going ahead and transferring the energy, right? But instead, we have waves, right? So we have waves that transfer energy. So that is the big thing on here, is that we have waves to go ahead and to transfer our energy. The next one is going to be conduction, right? So conduction is going ahead and having direct contact. Right, so if you have direct contact with something and you're transferring the heat with direct contact, that is going to be conduction. So what happens is that in conduction, right, we have our molecules, right, and then once one of them gets heated, right, and excited, right, you have to remember that heated molecules will move faster. So since the heated molecules are moving faster, what it'll do is that it'll transfer the energy to its neighbor right next to them, right? And it goes ahead and it bumps into them, and it goes ahead and it passes along that energy, right? So conduction happens through direct contact, and it's these molecules that are just bumping into each other to go ahead and to transfer that energy. So very commonly, conduction is something that you'll see in solids. So conduction happens best in solids. It happens even better in metals. Those are the types of things that get hot really easily. So anytime that there is like a direct touch to something, that is what you're going to see is conduction. The last one is going to be convection. Now convection is basically, it's going to be a heating pattern, really. So in convection, what we have is that we have a heating pattern that starts with a heat source. So you can have your, let me draw that nicer. So you can have a fire. So we can go ahead and let me grab something. So if you have a fire that's happening on here, right, and our fire is going to function as our heating source. And so in this fire is going ahead and it's heating pretty much the air around it, right? So the fire is going ahead and it's heating up this air around it. And we have our air molecules, which I'm going to go ahead and we're going to kind of have on here. So we have this fire, and this fire is going ahead and again heating molecules, right? And heated molecules go ahead and they travel quicker, right? And since the heated molecules are moving faster, these molecules become less dense. And the thing about less dense molecules is that less dense molecules tend to go ahead and come up, and they are going to go ahead and they are going to float up, right? Because they're less dense, they're lighter, and they're going to go ahead and they're going to float up. Now, the molecules down here or up here are cooler. And cooler molecules tend to be more together. So cooler molecules are going to sink, right? So we have two things that are happening, right? We have our cooler molecules that are sinking, and the ones that are closest to my heat source are going ahead and they're rising up and becoming less dense. So what happens is that we have this continuous pattern that's going on of rising and falling, rising and falling. And you'll see that convection is actually something that is very common in air or gases, and it's also common in liquids. So liquids and gases, super common for convection to happen as long as it has a heating source. Now, if this fire was not here, right, then convection would stop, right? And then if convection stops, we will no longer have that heating and cooling cycle that we have going on. Okay, so now that we covered some of this, we are going to go ahead and we're going to review some of the situations that we see on the study guide. I probably won't go through all of them since I did go through a few, but just as a review for you, we want to go ahead and we want to be able to make sure that we are able to recognize some of these situations, okay? So we are going to go ahead and let me change this to my mouse. So we are going to go ahead and we're going to look at this situation right here. So we have a heating lamp, right? And since my lamp is going to be my source of heat, heating lamps are usually really hot and they usually give warmth. And heating lamps usually give warmth in the form of rays. And this is what we have as or radiation. And all you would have to do is that you would have to say that this is radiation, right? And that the lamp is giving off heat in the form of waves, right? The next thing is that we're going to go ahead and we're going to look at this ice cube and on this spoon, right? And we have a heat transfer that's going ahead and that is happening here, right? The ice is going ahead and the spoon are touching each other, right? And then we are going ahead and we're passing that heat, right? From the ice to the spoon and from the spoon to the ice, right? So this is going to go ahead and to be an example of conduction. Since we have these radiation that's happening and the radiation from the lamp is being passed down to the air around it and to the spoons, right? Another thing that I would see is that the air might start a convection cycle. And this is the reason, this is kind of common in your atmosphere. We'll see that once something gets heated or air gets heated, it will go ahead and it will warm up, right? The air goes ahead and it warms up. It goes ahead and becomes less dense, rises up to the top, and then sinks back down. Except since your heat source is at the top, your air is probably going to go about to here. Then it's going to cool down and come back towards the heating source. So those are just a few things to kind of think about. And remember that for your version of the test, please make sure that you're able to go ahead and to drag and drop those arrows so that you're able to go ahead and to express those things. Now, most of these drawings have at least two of these things happening. For example, like this one, it's our fire again. So our fire and our air, like we did in our example, is an example of convection, right? And then we also have some radiation that's going ahead and warming this person's hand. So then you would go ahead and you would explain that as your heat transfer. This example right here is our hands, and we have a little bit of conduction there. And depending on what you think is in the cup, you might have convection. Okay, so this goes ahead and it relates to a couple of things. So I want to go ahead and I want to build some relationships, and we're going to skip down to some of the earth science stuff, and then we will go ahead and we will talk about how this relates to some of the math that we see later. So earth science things that you guys do need to know is the layers of earth. Earth has a few layers, as you know, right? So we have our outer layer of Earth, which is going to be our crust. So the outer layer, again, is our crust. Our crust, there are two types of crusts. There's oceanic, and there is continental crust. So we're going to talk about that real quick, and we're going to make sure that we label those in there. And I'm just drawing random ocean. So this will be oceanic crust. And then we have continental crust. Then the next thing is we're going to talk about some of the plate boundaries that you have in that. But just so that you guys know, oceanic crust is going to be more dense. So this one is more dense. And then continental crust is, continental crust is usually the less dense. And continental crust, you have to relate to land, while oceanic crust, you relate to the oceans, right? Next thing is, the next layer that we have is the mantle. Now, the mantle is pretty much our thickest layer of Earth. Oh, that was a little more orange than I would like. So this is the mantle, and I'm going to label all of these for you. So let's see if I can find a darker pen. So this is the mantle. This thing is lagging. And then this is the core. Now you have to remember that the core is the hottest part of Earth. The mantle, on the other hand, is a thing on Earth that is actually convecting. So since the mantle is convecting, you will see that convection is going to go ahead and convection is actually causing these plates to move, right? So now we have three types of plate boundaries on Earth. We have converging, diverging, and transform boundaries, right? So converging plate boundaries are plate boundaries that are heading towards each other, right? So if we have two land masses that are heading towards each other, or two oceanic things, oceanic crusts that are heading towards each other, that is going to be converging. If they are spreading away from each other, that is going to be a diverging. And then if they are sliding past each other, that is a transform boundary. Right, so those are the different types of boundaries. Now, these things happen for different reasons. So a converging boundary, right, is responsible for mountain formation and all of that, because two plates are going to go ahead and to collide with each other. A diverging boundary you'll commonly see in seafloor spreading. And then a transform boundary, you will kind of see some of the rivers move. And then that is the cause of some of your strike slip faults. Now, volcanoes, on the other hand, happen because of a converging boundary, and a special type of converging boundary called a subduction zone. And in a subduction zone, basically what we have is one plate will go ahead and will go under another plate in a converging boundary. So when we have one plate go ahead and go under another plate, what will happen is that some of the mantle will go ahead and will kind of leak up to the top. And since we have some mantle that goes ahead and leaks up to the top, you get the formation of a volcano. Earthquakes, on the other hand, happen whenever the plates move and there is some collision in the plates. Earthquakes will go ahead and happen. And if you remember from your maps, right, earthquakes and volcanoes usually happen in a very similar situation. So next one that we have on here is going to be, let me double check and make sure that I have everything. Okay. Density and convection. I already talked about that. Okay, we're gonna go here. Okay, so the next thing is conduction. So you have to remember that conduction is when two things are going ahead and that they are touching on one another. And basically what will happen is the exchange of heat. So the heat is going to go ahead and it's going to be exchanged. And when the heat is exchanged, okay, so the next thing is conduction. So the big thing about conduction is that we have basically two objects that are going ahead and touching. And when these two objects touch, what will happen is that they're going to exchange heat with each other. So this is very similar to what you guys did on Gizmo. If you have not done the conduction Gizmo, I highly recommend you going through this because you will have to go ahead and you will have to analyze a graph like this on the test. But what we see here is that we have our warm water and our cold water, and then over time you will see that these two pieces, they meet and that they are going to eventually be the same temperature. So when we're talking about what's gaining and what's losing heat, we have to look at our starting temperatures and then where they ended up, right? So the warm water, so first we're going to look at what we have on here, and we'll see that they kind of turn out to be either, let's see, 2, 4, 6, 8, 10, yeah, 24-ish degrees. So they end at about 24 degrees. And again, this is an estimation. And then we are going to kind of go ahead and we're going to look at where they started. So this one ended up at like maybe 42, 43-ish. And then this one started at 2, 4, 6, 8, 7 degrees-ish. So then if we're looking at those two, right, we're going to look at where these things ended up at equilibrium and how these things became equal. So we have the warm water that went from 43 to 24, so it lost heat. And then we have the cold water that went from 7 to 24 that gained heat. So you'll see in conduction that usually something will lose heat and something will gain heat, and they will do it and exchange that heat until it is equal. So that is the big concept about conduction. And so those are a few things to go ahead and to keep in mind when we're looking at those graphs. And again, making sure that you are analyzing those on there. Okay. And next thing is to go ahead and to talk about good and poor conductors. So a good conductor is something that will go ahead and will go through that exchange process and pass down that heat very quickly. So a good conductor will go ahead and will pass heat quickly. Oopsies. Right? A poor conductor is going to do it more slowly. So that is the big difference on there, is that a good conductor will do it fast, a poor conductor will do it slow. And that is just because the way the molecules are spread out, if they are bumping into each other quickly, if they're able to go ahead and they're able to get their neighbor activated enough in order to go ahead and in order to cause a change on there. Okay, for radiation, again, like we described, radiation is a wave. it is going ahead and it is passing down heat without touching anything. It does not need solid or liquid or gas to travel. Big thing is that it is a wave and it needs no state of matter. Right? And then make sure that you go ahead and that you look at convection, conduction, radiation, and check out that heat transfer in real life assignment so that you can go ahead and you can see those convection, conduction, and radiation deals. So where you can see convection in waves, where you can see convection in the atmosphere, where you can see conduction, right? So if it's very simple, putting your hand on like something cold, right, or putting your hand on something hot will go ahead and cause that transfer. The sun is an example of radiation. All of those things are things that you can go ahead and that you can talk about. But if you're not sure about some of these examples or need to review them, highly recommend it because you will definitely see some of those real life examples on the test. Okay. Last but not least, we're going to go ahead and we're going to go through these questions before I get to into the math. So density and convection, you have to remember that density is a driving force in convection. So you have to remember, I'm going to go ahead and I'm going to do it down here. That first of all, for density, you do need a heating source for density, right? So I'm going to go ahead and I'm going to do my mini fire again. Then I am going to have molecules that are close to this fire. And then what is going to happen is that as they get heated, they're going to spread and they're going to go ahead and they're going to float up and they're going to become less dense because they're going ahead and they're going to be at the top. Eventually, it starts cooling down and it starts getting more dense. So it's going to go ahead and it's going to cycle back. And so density and convection are very closely related because density will go ahead and kind of make that convection current flow, right? Conduction, like I said earlier, is going ahead and it's going ahead and passing that heat down. So again, I can have some excited molecules that are very spread out here, right? They are moving and they are bumping into things, right? But eventually one of these molecules are going to bump into another molecule that is still. That still molecule is going to pass down that energy all the way down. And when it passes down that energy, it gets them excited too. And when you have to remember, when molecules are moving, they are also being heated. So that is another big concept that you have on here. Radiation, again, I can have my sun. And radiation, again, happens through waves. So those waves go ahead and they transfer that heat to another object. So those are our big concepts that we want to make sure that we cover. Okay. Next is going to be some of the math stuff. I'm going to take my time and do a couple math problems for you, and then we will go ahead and we'll wrap this up. So first and foremost, before we get into the math, a big thing about before even doing the math is to make sure that you understand the variables, okay? So we have Q, M, C, and delta T, right? And those are all the variables that we see in our equation. Each of them stand for something, right? And each of them have a unit. Now, I would highly recommend that you know, right, these units. These units are super helpful. They help you match up what goes to what area of the equation, right? So first thing to know is that Q is going to be in joules. So anytime you see a J in the back, that's automatically going to stand for a Q value. If you see M, right, and we're talking about mass, that is usually going to be in grams. If we see C, which stands for a specific heat, that unit is joules over grams degrees Celsius. And then your delta T is your T final minus your T initial. So anytime you have two temperatures, you're going to have to go ahead and subtract those, and those are going to be in Celsius. So please make sure that you're paying special attention to the actual units that you have in your problems. Now, once you have your units, we're going to go ahead and we're going to pull them out and then plug them in to our actual equation. So we are going to go ahead and we're going to get started with our next problem. Whoops. Let's see. Oh, I just moved over a tab. It's all good. Okay, so next thing that we're going to do is that we're going to get started with this problem. And we are going to go ahead and we're going to look at this. So first thing, we go ahead and we read our problem, and it's asking us what is the specific heat capacity of 350 grams of unknown material if you need 164 joules of heat to raise the temperature from 20 to 45 degrees Celsius, right? So what we're going to do is that we're going to list what we have. So we have 350 grams. We have 164 joules. And then we have our 20 to 45 degrees Celsius. So we have 20 degrees Celsius to 45 degrees Celsius, right? And if we look at our previous slide, we can go ahead and we can determine, and we're going to look at our units that we have. And we have joules and grams and all of that there. Right, we're going to go ahead and we're going to look at those units and compare them to what we have on this slide. And we are going to go ahead and we're going to write these things down. So comparing that, we'll see that our grams is going to be equal to our M value. Our joules is going to be equal to our Q value. And this in here, some way, shape is going to be our T value, or delta T. So we have to remember that our delta T is equal to T final minus my T initial. Right, so I have to go ahead and I have to look at what I end with, which is 45 degrees Celsius. And then I subtracted from what I started with, which is 20 degrees Celsius. And if I go ahead and if I do that subtraction, I should get 25 degrees Celsius. Now I'm going to go ahead and I'm going to plug it into the equation. So I have Q is equal to MC delta T. And I'm going to plug this in. So I have 164 joules here. I have my M value, which is 350 grams. I have my C value, which I don't know yet. And I have my delta T value, which is 25 degrees Celsius. So I'm going to go ahead and I'm going to multiply whichever numbers that I have on the right side together. So I'm going to multiply 350 times 25. And when I multiply those together, I get 8,750 grams degrees Celsius times the letter C, because I'm bringing down this C that I have right here. Then I have this equal to 164 joules. I'm going to go ahead and I'm going to divide that. And then 8,750 grams degrees Celsius. And when you divide them, you should get a really small number. Should get 0.018 joules over grams degrees Celsius is equal to my C value. So that is what you should get on there. So that is what your C value is going to be equal to in this case. I'm seeing some mistakes in which people are plugging in the wrong thing in their calculator. So please make sure that you are always double checking what you are plugging in and making sure that you are plugging in the correct things, especially when you're dividing. And then don't forget that the M, C, and delta T are all being multiplied together. So I'm seeing some people that are trying to add and subtract, and all of these problems are all multiplying or dividing. You should not be doing any adding or subtracting. Okay, so over into our last problem. So in this problem, same deal. We are going to go ahead and we're going to read this problem, and then we're going to figure out what we have on here. So it says, find the heat that is required to raise the temperature of mercury from 57 degrees Celsius to 75 degrees Celsius. The specific heat of mercury is 0.14. And there is 25 grams of mercury present. So now that we are going ahead and now we're pulling out those amounts, we have 57 degrees Celsius to 75 degrees Celsius. And that is going to factor into our delta T. We also have our specific heat, which is 0.14 joules over grams degrees Celsius. And if I look at that unit, that is going to be equal to my C value. And then I have my 25 grams of mercury, and that is going to be equal to my M value. Right, so now that I have those, the only thing that I have to do is to make sure that I calculate my delta T. And again, delta T is equal to T final minus T initial, right? So then I'm going to go ahead and I'm going to subtract 75 degrees Celsius minus 57 degrees Celsius. And when I go ahead and when I just subtract that, I should get 18 degrees Celsius. And that is going to be my delta T in this case. So now I'm going to go ahead and I'm going to set up my problem. And again, I'm going to go Q is equal to MC delta T. I'm going to plug in my values. I did not see a Q value on here, so I'm going to leave that as Q. Then I'm going to have my M value, which is 25 grams. I'm going to have my C value, which is 0.14 joules over grams degrees Celsius. And then I have my T value, which is 18 degrees Celsius. So now that I have all of these values together, what I'm going to do is that I'm going to multiply them. So I'm going to go 25 times 0.14 times 18. And what I should get is my Q is equal to 63 joules. So that is what you should get on there. And again, make sure that you are plugging in those values correctly and that you're looking at units in order to go ahead and to get things to match. But other than that, that is all that I have for you. If you have any questions, please feel free to email me and let me know.